There we go. Yeah, and I'll always see people, like, again, for those of you that are here, this doesn't really apply to you. And you could say, well, okay, those watching the video that aren't in class, but they don't watch the videos. And I know that because I get all these YouTube statistics. And when I have a video posted and it says there's one view for 3 minutes, and I have 5 people telling me they watched the whole lectures, it's pretty obvious it's bullshit. So anyways, that doesn't apply to anybody because no one's watching the videos anyways. Do we have any last questions before I get going? All right. All right. So this is what we were talking about last time. We were going through genetic operators. We were talking about crossover and mutations. And we started with talking about the binary representation, then we switched to integer representation. And yeah, so we were on with integer representation. We talked about swap mutation. This works really well for also permutations as well, right? So when you do a mutation, okay, crossover, okay, yeah, mutation. Single point mutation, you pick an index, you change it to something else, okay? And what we were talking about last time, this is where we ended last time. What we were talking about last time was, well, when you select an index and you want to replace it with a new value, like it's not a binary representation. When it's a binary representation, you just flip it, right? If it's a 1, make it a 0. If it's a 0, make it a 1. And obviously, a binary representation doesn't literally need to be 0s or 1s. It could be anything that has one of 2 values. When you have an integer representation, so let's say your allowable values are between like 0 and 9, for example, and you pick an index and it has a 4 in it. Well, what number do you replace it with? Well, roll the dice, right? Pick any number between 0 and 9. But you might say, well, what if I know I'm more likely to want 7s in there? Well, okay, you can adjust your mutation accordingly. Like, go ahead, do it. But like we were talking last time, we got to be careful with how much bias, like our own bias, we add to the search. I'm not saying it's necessarily a bad thing. I'm not saying it's a good thing. I'm saying empirically figure it out. Try it, see what happens. Try it without that idea. Was it better, was it worse? Was there no difference? Whatever. And the example I used was when I was randomly generating those strings and I wanted those strings to be more likely to be like English words, I know that in English, some letters are more common than others. So if I were to randomly generate or randomly pick a letter, I might want to pick it from the distribution of what the letters look like the actual letter distribution of your typical English sentence. Okay, swap mutation. This one's great for a permutation representation. Pick 2 indices and swap their values. That's it. For certain problems, this might be great. If we're problems where the order of things don't really matter, then that probably isn't going to make much of a difference. Where order does matter, it'll make a big difference. If, yeah, you need unique values in here, this is great because you're not adding or removing any information. You're just kind of moving around where it is. Creep mutation. This is when you pick an index, and let's say it has the number 7 in it. I want the mutation to pick a new number, but I want that number to be near the value it already was. So if it was 7, I want it to be 6 and 8, maybe 5 and 9, but not really more than that. I mean, I can make it this nice like normal distribution of likelihood to pick which value. So like it could pick a 1, but it would be very unlikely. So I could do something like that. That's called a creep mutation, where this mutation is often used in situations where values within the chromosome represent ordinal attributes. So where there is an ordinalness to it. Here, I'm going to put this around. Now remember, like last time, there's 1, 2, 3, 4, 5, 6, 7, 8 people in here. If there are more than 8 names on here, we're going to have a big problem. When you're done, just pass it down. Cool phone. Genetic operators for permutation representations. All right, permutation representations are those that consist of different orderings of values from some predefined set or multiset. Multiset just means set, but you can have repeated values within it. So like TSP was a really good example. The representation we talked about for n queens is another good example. There are some of the previously discussed genetic operators. From those, there are some that are really appropriate and some that aren't really, right? Like single point mutation will probably destroy your permutation. So what crossovers work? Well, these are tricky. So what's the first one here? Order crossover. Now listen carefully, because these ones are tricky. I wouldn't say that it's critical for you to have a complete 100% full understanding of this after I'm done talking about it. I want you to, but if you don't, here's what I really need to make sure your takeaway from this is that you get the idea, the intuition of what it's doing, so you know that it's safe for permutation representation, and it gives you ideas on how you can make your own. So here's order crossover. Select two indices at random. Copy the elements between, remember this is crossover, so this is for two chromosomes. So you select indices, what did I say in this example? 3 and 7, in the example we're about to see. Select two indices, copy the elements between the selected indices to a child. Copy the missing elements in the child from the other chromosome in the order they appear after the selected index. And this is, like I was saying, best described with an example. So one, select two indices at random, 3 and 7, 0, 1, 2, 3, 4, 5, 6, 7. So here it is 3 inclusive, 7 exclusive. So let's say I cross this over. All right, so this goes to the child. Copy the elements between the indices. So typically larger indices are not included. Okay, typically the larger index is not included, yeah, like excluded. Here are the elements at indices 3, 4, 5, and 6. So 3, 4, 5, and 6 are copied over. So we see 4, 5, 6, 7. Copy the elements from the other parent to the child in the order they appear, starting at the larger index. So we wrap to index 0 where necessary. Here the copying would start at index 7, so I guess the 1, because it would be from the other parent, right? So index 7. We wouldn't do the 8 because that's from the same. This is where the crossoverness comes from, right? This part here is here. So from the other parent, we start here, index 7. The 1 would be copied to the child as it is not contained within the child chromosome already. So 1, there's no 1 in here, so we can copy the 1. We go to the next one, 4. But a 4 is already in here, so we don't do it. All right, the value at index 8 is 4, but would not get copied since it already exists in the child. The next index would be 0, as there is no index 9, so we wrap back to 0, right? As there is no index 9, which contains 9. Thank you very much. Are there, how many names did I say? 1, 2, 3, 4, 5, 6, 7, 8. Hey, nice. All right. Yeah, 0, as there's no index 9, which contains 9, thus we copy it to the child. So the 9 gets copied, because there's no 9 in the child yet. The 3 would get copied to index 0, though, because we wrap back around. The 7 does not get copied, because it's already in the child. The 8 would get copied. The 2 would get, how far have I gone? I've lost track of counting. Yeah, the 2 gets copied. And well, then we're done after that. And conveniently, 6 and 5 are already in there, right? Happy? We would repeat this process for the other one as well. So we would have 8, 2, 6, 5, and then we would not copy the 8. We would copy the 9. We would copy the 1, not the 2. We would copy the 3, the 4, and not the 5 or the 6. That's how it would go for the other child. Happy? Sad? Awesome. So this is order crossover. I like this one. It works well. I like this one for TSP because remember we were talking about destructive crossovers? When doing, like this crossover will preserve a contiguous chunk, which is a good thing for something like TSP. Presumably, if we've got a chromosome in the population at some arbitrary generation, let's assume it's some arbitrarily large generation number, contiguous chunks are going to be probably reasonably good, so we want to preserve those contiguous chunks. Cool? Cool. Partially mapped crossover. This one I always forget, so bear with me as I remember it. This is another, there are two very popular crossovers for permutation representations. PMC is order crossover and partially mapped crossover. So this one's tough and hard to explain in words, but an example I think will help. Select two indices at random, 3 and 7. Okay. Hold on, do I have that? Yes, okay. Yeah, you can see it starts to get a little crazy. All right. Copy the elements between the selected indices to a child. So far, it's the same as order crossover. And pause on this. Another thing with order crossover too is not only do we preserve a contiguous chunk, but like, imagine for example, like when we were copying over to here. So in this child, let's say this is a reasonably good child, meaning the order in which we visit these cities are reasonably good. So a contiguous chunk, awesome, we preserved it. But like, let's say, and remember with TSP, it doesn't really matter what the starting index is, right? It really doesn't matter because it's a Hamiltonian cycle. You could start at any of the arbitrary indices, like cities along the way, and it's still a cycle, right? Yeah? So if I were to say go from city 1 to 4 to 9 to 3, let's say that's a good chunk. Like if I were to draw this, imagine I'm just going to draw some arbitrary, let's say this is from city 1 to 4 to 9 to 3, okay? And there might be more cities around here, I don't know. But let's say this is, in the bigger picture, there's a much bigger graph, okay? And for whatever reason, this is a pretty good path. Now, because with order crossover, because I'm going like in order as I go, but I might skip some. If I were to say, do I have a different color? Let me see if I have another color. I do not. There's a blue one here. Let's see. 1 to 9 to 3. When doing order crossover, consider that the child, instead of getting 1, 4, 9, 3, in that example, we would have gone 1, 9, 3. We skipped this one out. And this was clear, like the black line, that was part of a good path, right? To show that it's some bigger, part of a bigger path. But because we're doing it in order, and the order matters, and maybe we're skipping a city like we skipped this city here, here to here to here is good. It wouldn't be crazy for here to here to also be pretty good too. So this really is a good crossover for something like TSP. Now, if we compare this to partially mapped crossover, you're going to see we start to kind of jumble around a little bit. Okay, partially mapped crossover. It starts the same as order crossover. Okay, I selected this, go to the child. And we're going to repeat the same process for the other child, just from the other parent. Start at the first selected index in the other parent. Copy non-copied elements in the child by finding the index of the element that exists in the child at the index of the non-copied index. Makes total sense, right? So here, the value of 8 was not copied and exists at index 4. So here, 0, 1, 2, 3, 0, 1, 2, 3. Oh. See, pardon me, I always got to remember this. Here, the value 8 was not copied and exists at index 4. I don't think it exists at index 4. 0, 1, 2, 3. It exists at index 3. The value in index 4 of the child is 4. 0, 1, 2, 3. Yeah, I've messed up. These are supposed to be 3s. If someone wants to submit a pull request to fix this, be my guest. The value at index 4 of the child is 4. Okay, let's assume it is at index 4. The value of 4 exists at index 8 in the parent. 0, 1, 2, 3, 4, 5, 6, 7. Yeah, okay. I'm off by 1 apparently. Let's just go down to the picture. So, we've got the 8, right? We go to the other parent and there's a 4. The 4 is here. So we copy the 8 to where the 4 would have been. Do you see? Okay? So not where the 4, we copy the 8 to, the 4 is there. Why did we go there? Index 8, oh my God. Let me reread this. I'm all out of whack now because I have it written down wrong. So let's assume we start counting at index 1 for the sake of this example. Here the value of 8 was not copied and exists at index 4. Okay, 0, 1, 2, 1, 2, 3, 4. Okay. The value in index 4 of the child is a 4. Yeah. So thus the value of 8 is copied in, the value of 4 exists at index 8 in the parent. Ah, yes. There we go. Okay. So we say there was a 4 there. I want to find where the 8 would go that was where I put the 4. All right? I'm seeing a lot of blank faces and I get it. We'll get this. We'll get this. So I copied this from here, okay, from that parent. And at this stage I go, okay, well, if this is going, like, there's 2 children, right? I'm only showing 1 here. This would go over to here, right, if we had another child, right? Imagine there's another child up here. Remember with crossover, you kind of think of it going like that. So the 4 is there. We go to this parent, right? So from this chunk I go, okay. Like, how about this? Imagine this was 2-point crossover. If this was 2-point crossover, I would have taken this and put this there. I basically would have overwrote this and put this up there, right? But this isn't 2-point crossover because we have a permutation, okay? This part shouldn't concern any of you. This part should be like, yep, absolutely. So imagine I was like overwriting this over here to the child, okay? So that's where the 8 would go. So, the 8 needs a home. So I go, okay, from this index, there's a 4 there. So I already have a 4, okay? So the 4 from where this one is, like if I were to, remember, this is from this parent, and if this was 2-point crossover, there'd be a 4 here, but I can't repeat the 4, okay? There's already a 4 in there. So I go, well, I need that 8. So where do I put that 8? Well, put it where the 4, where that duplicate 4 would be, right? So where is it? Oh, there, put the 8 there. The 2. So where does the 2 go? Well, the 2 is where the 5 is, and the 5 is, okay, here. All right, and now I think here we've got a bit of a game we got to play. So 2 to 5 to 5 to 7 to 7. We have to keep doing it until we find one where there's an actual duplicate. So the 2 goes to where the 5 is. Well, I already have a 5, so that's safe. So where's the 5? Okay, there. And what matches up with the 5? Well, the 7. Well, where's the 7? Here. Ah, okay. So I could put the 2 there. So you end up having to play this bouncing game until you find one that doesn't exist in the child yet. So if we do the 6, well, the 6 and the 6 is fine, I think. Does this? Yeah, the 6 doesn't need to change. And then the 5, well, the 5 to 7, where would the 5 go? Well, oh, we already have a 5, yeah, so we're fine. And if we play it out, and then once we're done with all the conflicts, you just fill in the blanks. Like the 1 can go there, and the 9 and the 3 can go, because we've dealt with all the conflicts. The trick with this one, I know I've explained this poorly because I got all thrown out of whack because the indices I started counting at 1 for some reason in this example. Did anyone submit a PR? No? I'll do it later. It's fine. The key is, where I would want to put, I copy over the 4. How about this? What if let me put it this way. Here, I have a problem. Because there's a 4. Why is it not letting me draw there? Where's my cursor? Because there's a 4. I copied the 4 over, but there would be a 4 here, right? And then there's also a 7. So that's like what we're resolving, those repeats. And how do we do it? Well, you end up bouncing around until you find the 8. Okay, well, what matches up with the 8? The 4. Well, where would the 4 go? If there's a 4 in here, okay, I've got an 8, and I'm crossing it over with a 4. Now, there could be a 4 in this part. I don't know yet. That's kind of like what happened with the 5 and the 2. But there could be a 4 in here. I don't know yet. But here I go, okay, well, where's the 4 in the other one? Ah, it's outside there. So I can put the 8 that's being replaced to where the duplicate 4 would be. Okay, I've effectively found where the duplicate would be. If I move a 4 here, I find where the other extra 4 would be. So I replace it. The 2, okay, well, the 2 to the 5 to the 7 to, oh, we're outside. So I found where that extra 7 would be that we'd crossed over. I can replace that with the 2 and so on. If you're not happy with this, it doesn't, like I said before, we don't need to be experts on this at the end. There's no test to be like explain partially mapped crossover, okay? If you want to use it, use it. But as you can probably see when comparing this to order crossover, it's a lot more, it definitely feels like it's going to be more destructive because things are going to get really moved around within the search space, okay? As you can see, like, well, the 4 suddenly gets thrown over there. Some orderness is preserved if we get lucky, but that's just, in this example where we had like the 9 and the 3 stayed, that was just like luck by nature of how it was laid out. Oh yeah, there's a cycle crossover. Forgot that guy. So this one's a little bit more destructive, I would say. But that's not necessarily a bad thing. When doing something like TSP, remember last time we were talking how as evolution goes on, having a little bit more exploration in your search is kind of good. You want your algorithm to be able to make large jumps throughout the space in case it's kind of stuck at a local maximum or minimum, depending on what you're doing. So we're at like a local good area. And if your search keeps exploiting what's good, it's never going to leave that area. Where if we have something that's rather destructive, it might be able to like throw us way out over there and find something potentially better. So this is not necessarily a bad thing. Be very aware of that. Okay, cycle crossover. Select an index at random. Identify the value at that index in parent 1. Get the value at the selected index in parent 2. Find the index of the value in parent 1. Repeat until the whole cycle is found. So you basically go through and you find a cycle. Exchange the elements at the... So we find a cycle. 1 to 9 to 9 to 4 to 4 to 8 to 8 to 1 back to 1. So we found a point where we have a unique... We have matching indices. We will do this until we find a whole cycle. These cycles can end up being huge or small, but we do this until we find a whole cycle, where you always go to corresponding, like, respective indices. So 1 to 9. Okay, where's the 9? There's over there. Where's the 4? It's there. Where's the 8? It's there. Where's the 1? We found a cycle. Awesome. I know that I've got a 1, 4, 8, 9. 1, 4, 8, 9. The values and the indices must match, and the values in those indices must be equivalent. I can flip them. There's no risk of repeating. You agree? Okay, what do I have here? Oh, and then here's another cycle. 2 to 3 to 3 to 7 to 7 to 5 to 5 to 2 to 2. Cool? And then we've got another one here, 1. So you only need to do it with one cycle. You don't need to keep finding cycles. You would just find one cycle and do that as your crossover. This, to say this really is, you might say, well, this isn't that destructive because look, you've got like a nice contiguous chunk here, right? It gets preserved. Yeah, but that was just dumb luck. There's nothing intrinsic about this crossover that is very preserving to the orderness. You might get lucky, you might not. That type of thing might be what you like. Something that can preserve order, but doesn't necessarily have to. At the end of the day, like everything in evolutionary computation, it's hard to come up with hard rules about anything because at the end of the day, you pick what works. That's it. That's all you got to do. Cool? Cool. Mutation, swap mutation works really well. Do we have any questions? Insertion mutation, it's kind of like swap mutation, except you just kind of like shove it in between. There you go, there's an idea. Scramble mutation, select a subset and just shuffle. There you go. It's kind of like a super version of swap mutation. So you pick a chunk and then you just shuffle them up. And there the order is 3, 5, 4, 2. Why? Because it's just random. Cool? Inversion mutation. This is kind of nice for something like TSP. You pick a subset and then you reverse the order. Cool? Cool. The point, I'm going to keep emphasizing this. The point of me showing you these genetic operators is not for you to go, that's the genetic operators I should be using. No. It's to just show you what works, and then you come up with your own ideas. And if you don't like any of the ideas you come up with and you like these ones, go ahead and use them. If you don't like any of these, come up with your own. Great, it doesn't matter. It's up to you. The point is not that you memorize these and you know them and you've added them to your tool belt. I mean, cool, by all means do that. But none of this is to say that these are the mutations. These are the crossovers that you should use. Although these three are like basically the default ones anyone uses for permutation representations, by the way. But other than that, really do whatever the hell you want. That's the spirit of this whole course. Questions so far? Thoughts, concerns, comments? I'm sorry about the partially mapped crossover. I can't figure it out, so don't worry about it. Scramble mutation, inversion mutation, genetic operators for floating point real numbers. So now this is where you start to get a little hacky. And to be clear, there are some, this would be like showing you what you could use for genetic algorithms to make it work well with floating point numbers. And when I say work well, really what I mean is work with floating point numbers. There are, like, genetic algorithms are really not, it's not that they're bad, it's that there are similar algorithms that are specifically designed for working with the real numbers. Where genetic algorithms, not so much. Genetic algorithms excel more in like a very discrete space, where this is gonna, like, so things like PSO, differential evolution, evolutionary, I'm forgetting one, but nevertheless, there are evolutionary algorithms, or more correctly, there's forms of evolutionary computation designed for real numbers. They're floating point numbers. Genetic algorithms, not so much, but we can do it, and this will give you a sense of ideas that you could play with. So yeah, real number, floating point real number representation consists of continuous values. They are bound by the computer's ability to represent real numbers as floating point numbers. There are many complex genetic operators for floating point number representation. Only a few relatively simple, popular ones are discussed here. In practice, there are other forms of computation that perform better, like I was saying. Crossover. Two broad ideas. Discrete. This is where the offspring actually have value. Now, we got to be careful. When I say discrete, I don't mean discrete in the context in which I literally just said discrete, where GAs are great for discrete spaces. No, discrete here means the data from one parent, the data from the parents are actually like preserved, where the intermediate, this is where the values are somewhere like between the values from the parents. You'll see what I mean in a moment. So single arithmetic crossover. So randomly select an index, average the value between the parents at that index. Great. So here I've selected, looks like this one. And I average them out. We get 0.5. There, you put it in both parents. There. There you go. There's a crossover. You could do this. This is an example where you do it with a single value. Of course, you can do it with arbitrary number of values. I think that, there you go. Right? So here it's like single point crossover, except instead of exchanging the values, which you could totally do, nothing is stopping you from doing single point crossover here. Right? Okay? But this is an example of an intermediate crossover. So like a discrete one would be here, pick them, but exchange them. But the intermediate is pick them and average them out between the two parents. Here, average them out between the two parents. We could exchange, do single point crossover or 2-point crossover or n-point crossover. But here we're actually taking the values and averaging them out. What's neat about this is, well, the values end up being the same in the two children, which is neat. You do the whole thing. Whole arithmetic. There you go. Right? Sky's the limit. Have fun. Questions about this? Yes.
What happens though if you can't have duplicate numbers?
If they what?
If you can't have duplicate numbers.
With real numbers, well then you're effective. If you can't have duplicate numbers, then you would need to, that would be tricky with the floating point numbers, because usually when you have a permutation, you have a set of appropriate values. So if you're dealing with real numbers, the set of appropriate values, that would be really situationally dependent. And in that case, something like this, obviously don't do it, right? Because the whole point of like, yeah, this allows duplicate numbers. So what to do in that situation? That would be very context dependent. It's hard to answer, but interesting question nevertheless.
Like what I was thinking with regards to like the one where you average them out, what you could do is you could take the value and then there's 0.5 does exist in the first one there. So if you look for where 0.5 is on the parent versus where 0.5 is on the thing, you could take the two and switch them.
If you're doing that, that's kind of like an interesting combination of like not really a swap mutate, but you're kind of like doing a swap mutation and a crossover at the same time. That's an interesting combination. And by all means, if that's going to work for your situation, by all means. By the way, this is an entire aside. If you look at your midterm grades, because I had to submit them, I don't know if they're available yet, to be clear. But when they become available and you look at them, remember the design of the course. Like really what you're looking at is, at this stage, the maximum number of points that you could have gotten is like, what, 25, I think, because of the assignment. And if you just chose not to do assignment 1, which is entirely fine because of how the point system is designed, and you're like, how come I have 0% in the class? Well, because you haven't got any points yet. But that's just, the nature of how it is. So don't freak out, because you should be aware. And also if you're like, well, it's 25 points, but the class is actually only out of 100, so shouldn't it be a bit, I'm not going to do all that calculation at this stage. Just be aware, like the midterm grade for this course, given how I'm doing it with the points and how you can get more than 100 points, but it's still capped at 100 points or 99 points. That grade is going to be like kind of bullshit, right? I have to submit something, so there you go. All right, back to this. Mutation. Okay, uniform mutation. Randomly selected index. Replace the value at the selected index by a value from a continuous uniform distribution within some range. This is a really fancy way to say, let's say, I wish I had a picture of an example. I picked the value. Now, I could do this any way I want, to be very clear. But the uniform distribution, we all remember what a uniform distribution is, right? Where I roll the dice and I'm equally likely to get any value between A and B. Equally likely, okay? So maybe I'm doing it such that I select an index and I want the values in there to be between 1 and 2. I roll the dice and I get 1.71211112111. Great, awesome, cool. I want the uniform distribution to be based around the current value in there. So if the number in there is 1.5, well, maybe I want to pick a number between 0.5 and 2.5. And I have a equally likely to pick between any of those. Great, cool, awesome. Uniform mutation. Pick a number where the chance of select an index, replace it with a number that is equally likely to be any values between some range. Cool? Well, we can have like a Gaussian version of that where, okay, yeah, same idea, but now I want you to be more likely to pick, now in this example, the blue one. Let's use the blue one because that's a nice one centered around 0, and the red one is as well. Here, and I can set these values. These are just the parameters for the normal, the Gaussian distribution, right? If you don't remember what that is, just basically, this is like what it's centered on, right? So it's centered on, yellow, red, and blue are centered on 0, -2 for the green one. And the value here, that's the variance or standard deviation if it's squared. I can't remember. Come on, you've taken stats more recently than me.
Standard deviation squared.
It's the
Variance is squared.
All right, so there's a variance. Great. The bigger this is, the fatter it gets. That's it, okay? So here, if I'm looking at the blue one, and I'm replacing it with a number, so I find an index, there's a number in there, I don't give a shit what it is. I want to pick a new number to pick in between there. Well, I'm going to roll the dice, but I'm going to be more likely to get something near 0 than I am to get something near -1 and +1. And a hell of a lot more likely between -2 and +2 and so on. Now you can also do it such that this value is centered on the value that already exists in there. So let's say the value 0.75 is in there. Well, I pick a number and then I roll the dice, get a number from this distribution, and then I just add that number to whatever's in there already, right? Does that make sense? Yeah? Cool. If it's like, am I missing something? Is he over-explaining this? This seems really freaking obvious. Yes, I am over-explaining it. It's random number generation. Do you want it to be from a normal distribution or do you want it to be a uniform distribution? It's just as easy as that. Self-adapted mutation, a non-uniform mutation, but the value variance of the, this one's actually kind of neat, where this is actually pretty neat. And it opens up a brand new idea that we haven't really thought of yet, is what if the evolutionary search is modifying the hyperparameters of the evolutionary search? So the chromosome, whatever it's encoding, also includes two new pieces of information in the example of the Gaussian distribution. What if the chromosome also includes, and this will work well because this is a chromosome for real numbers or floating point numbers, and these two values are floating point numbers, where we pick the mean and the variance are part of the chromosome. Meaning the chromosome will say, when I do the mutation, the chromosome, and I need to pick a random number, the random number generator will be told, pick a random number based on the chromosome's mean and variance value. Meaning that the chromosomes are being evolved, those values can change, and it's almost like the evolutionary search is optimizing both what the problem's being solved and what hyperparameters make the best sense at that given time. Because remember, these values can change over time, where maybe a high variance is really good at the end of a search, but bad at the beginning of a search. Cool? Isn't that neat? I think that's pretty cool. So now you have the algorithm is like, it's given a little bit more control of itself. And as soon as you do something like this, as soon as you give something the ability to be self-referential, that's where interesting shit happens. Things like this statement is false. We all know that one, right? The statement is referring to itself. And in doing so, we've created a bit of a problem. We've created a statement that is, it's not correct, it's not incorrect, it has no ability, it's like inadmissible.
It's a paradox.
Exactly. It creates a paradox. Which is funny because us humans, we love to put things in these nice categories, right? Well, things are either true or false. There's no such thing, well, what's about this statement is false? Is it true? As soon as you give things self-reference, that's where things get fun. So this is always fun to think about. Any questions about that one? Now, genetic operators for tree representations. So, I believe the next topic is, no, all right, we get to genetic programming next. Next. Usually with genetic programming, we have tree representations. And we talked a little bit about tree representations before to show you how it can describe like a program or some mathematical expression. So let's say I have two chromosomes. This one represents the expression 2 times pi plus x plus 2 minus y divided by 5 plus 1. Right? Like it's a big expression. What it means, what it's trying to represent doesn't matter, but that's what it represents. Let me draw it out. So we have 2 times pi plus x plus 3 minus y divided by 5 plus 1. Well, I'm just going to simplify that. No, 5 plus 1. Even though, like, obviously we know that's 6, but let's just leave it like that. That's what the left tree is, right? Did I do anything wrong? Does that look right? Yeah. And the other one down there is a times 3 times 3 plus y plus 12. Again, I know I can simplify this, but I'm not simplifying this on purpose. Can you see that, or did I write it too low? Whatever, there's an expression here. And I just say, okay, do crossover on these things. You're going to go, what is, like what? That doesn't really make any sense. Well, it makes perfect sense if you've got tree structures. All you do is you pick 2 nodes. Now this, we have to be careful, because this is an example of what we call untyped GP. Even though it's totally a misnomer because it is typed, because it only has one type. Really, it should be called like single type genetic programming, but they call it untyped for some stupid reason. All of the values in here are numbers. Whether we're looking at a terminal, which is something like 12, the literal value 12 is a number. Y, that's some variable representing a number, or the operator plus, which takes two values and gives you another like number. It takes 2 numbers and gives you another number. I don't give a shit if it's a number from a variable, a literal, or some other operator. I don't care. It's numbers. This is all numbers. So when I do this, I pick the divide, I pick the multiplication, and I just swap them. So this goes there, and this goes there. And there we go. After doing this, I'm not going to write the expressions because we're running out of time, but I could. Now, this enables a really easy way to do something like crossover on mathematical expressions, which is pretty crazy. Now, we got to be careful because we could have something like typed genetic programming where you might have Booleans and numbers and other types mixed into these expressions. That would be more like if you've got like a bona fide function, like a program, like if then else, right, where there's Boolean conditions, we're doing comparison operators where Booleans show up. Well, you got to be careful doing your crossover because you can't take something that returns a number and put it to an area that's expecting a Boolean, because then it would be not type safe, and we've got a big problem there. It won't work. So you'd have to be careful on that particular situation. Yes?
Would it also be possible to do genetic programming on something called loops?
Yes, you can. Typically, so we have to be, so yes, there's something called linear genetic programming, which we're not going to get into, but you totally could. Usually what you would do instead is you just kind of like rely strictly on like recursion. But yeah, you totally could do something like that as well. Any last questions before we wrap up? Awesome. All right, see y'all later.